Yo. What's up, everybody? Welcome back. Today we are working on our virtual GPU, and today's task is trying to get GPU memory mapped into a user space process. So the idea here is that we have this GPU that we've been working on. It's integrated into the QEMU virtual machine. We have like a kernel driver that exposes like typical GPU driver APIs for like kernel mode setting, as in like if we want to draw each pixel onto the screen by hand in the CPU, we can do that now using like a standard interface. And we've written a test application that we can use to demo that. So if I look at dev.dri card 1, we can go here and we have like our little application where we're drawing a smiley face and he blinks sometimes, right? Nothing too crazy. Now, we've been working a little bit towards trying to get a 3D rendering context set up so that we can like implement like an OpenGL driver for this thing. And one of the things that we have to do when we're doing 3D is like upload data to the GPU, right? And what we've been doing up until now in terms of like GPU object sharing is we've been doing something along the lines of in the Linux kernel, he can allocate this thing called like shmem, shared memory. And he can create like this like virtual address space of shared memory. So this is going to be like, some address, you have like a pointer to this thing in your code, and you can like just like write pixels into this thing, right? But what actually happens is this gets like kind of like paged into like many pages, and then this gets the pages are kind of like wherever they sit in physical memory, right? Then when we like interact with this buffer from our GPU, what we could do is like the GPU has like a view into like the whole host memory space. So our GPU will like kind of look at like this, and he goes like, oh, okay, well, I know that like the first part of the buffer is here, and the second part's over here, and the third part's over here, and the fourth part's over here, which is like kind of annoying, especially as we start implementing more and more features on the GPU side. It would be nice if the GPU had like a contiguous view of some form, so that he didn't have to do all of this like management. Also, kind of like in the mental model of us trying to make a GPU to understand like a real GPU would probably allow people to write data into like his memory. So instead of using like the CPU, like the host memory where the card is, he kind of wants like GPU memory here, GPU mem here. And what would be ideal is if like we had like some sort of view into like GPU memory where this is like vertex buffer and like I don't know, like texture, right? Like it would be nice if like we just had like contiguous slices of memory that weren't even related to host memory. Now, if we do that, then we have a problem of how do we actually like upload data into these segments? And so that's what I want to work on today is like a user space application. This is like all in the kernel here. What we want is we want to like actually go one level up, user space. We want him to be able to kind of see this memory as if it was normal, like just a normal pointer. And that should be doable. There's this thing called mmap, right? Which, is like something like this is like, I think this is how people get memory at all. I'm pretty sure that like allocators use mmap under the hood. I'm not 100% sure on that. But this basically says like, hey, let me get a pointer to something, and how those pointers are resolved is kind of like up to the kernel. So you can do things like mmap a file, right? You can open a file, and instead of calling like fopen and reading and seeking and all the normal stuff that you do, you can just like mmap the whole file into memory. And what happens is when you like try to access that memory, a page fault handler will trigger on the kernel. He'll go like, oh, what's at like address like 0x100? I don't know. And he'll like call the file system driver for that file, and the file system driver will be like, oh, okay, like let's like find out what lives there, and he'll like put that memory in the right spot, if that makes sense. So we can do something similar where when we access some memory that we've mmapped from our GPU, our driver will go, oh shoot, how do we access that stuff? And what I'm thinking is that PCI, which is like how our fake driver is hooked up, or our fake GPU is like connected, he's implemented as a PCI device. PCI has these things called bars, which is like base address register or something. And what these basically say are, here I would like a segment of memory that we can like read and write to that will interact with me in some way. And so he can like kind of like choose how to respond to writes on his bus. And so what we've done right now is we have like bar 0 has like basically registers. And so we have like this like set of registers that we can allow to like set like command and like args go in here, right? And so what I'm thinking is we could add a command that's like called like map. And this command can say in bar 1, which doesn't exist yet, we can say I would like to map this resource. So say we have like this like texture, right? We have a texture that like a user wants to upload. We can ask the GPU to like allocate this texture, who will live in like GPU memory somewhere, right? GPU mem. And what we can do is this is going to have like an ID. This is like resource like 1. And if we want to write to like this location of this, we're going to resource 1 plus offset, right? Essentially. And what we can do is our map command can ask, he can say, hey, can you put this page, like this section of data, can you put that in bar 1 at like offset something, right? So he can like kind of like put like this here and like this part here and this part here, right? Whatever. And so what I'm kind of thinking is that like the kernel will kind of manage what he wants to be mapped, and then he will just ask the GPU to do that mapping, right? So this could be like completely non-contiguous. We might have like other things from other resources in there. Maybe you're like uploading like a vertex buffer and a texture or something, and those will just kind of be like scattered around in this bar. It's kind of how I'm thinking about it right now. I don't really know how to do that, but we'll figure it out. We'll figure it out. So the goal for today is basically to do this demo that we're doing already. This one. Right? But instead of the data living in CPU host memory, I want that to live in GPU memory. So if we get to the end of the stream and we see this again, that's a huge win for us. And if we don't, then, that's fine. We'll live. So I think the first step here is to update the buffer that we do when we're doing this like little demo app. We should force that thing to be in GPU memory. And then once it's in GPU memory, we will see all of the places it falls over and figure out how to work with it from there. That's the plan. That's the plan. Let's get moving and grooving. Okay, so let's go into probably like the kernel and open our GPU driver for this thing. And the way that our app asks for this like frame buffer stuff is this like create DOM function, which we are currently saying, hey, I would like to return a gem shmem shared memory object. And we're going to go, no, we don't want that anymore. We want something different. We want Sphero create, there's like GPU object somewhere, create GPU. Hold on, it's in here somewhere. Here, derm gem Sphero create, that's what we called it. That's what we called it. So here when we create our DOM buffer, our DOM buffer will be backed by something on the GPU. Let's start there. So this just takes in a size, I guess. Oh, wait. He's jumping to the wrong function. Hold on. Is this... Oh, this function comes later, which is annoying. It means that we should move this down so that he can use this function. Fucking see where things need to be in the right order. Okay, we'll put him here. Okay, so he expects a device and a size. So dev here is just the device. And size is args size. And then we're going to have to get like a handle out of this thing. Surely. So when we do this in other places, we call handle create and put like this. So I think we just kind of go this way. So this thing expects a DRM file. So we just say file priv here. And he is going to come from this object that we made. So we're going to be like, hey, could you make us a hardware backed buffer, please? Sphero obj, I guess we'll call it. And then from here, we can say Sphero obj base, and Then he's going to want to output that to some sort of handle, which I think is in args, probably. Yeah. It is. It is. So args handle. Then we are chilling. And I think we can just return 0. Sure. I guess technically this can fail, so we'll do int rc is equal to this. And return rc, boom. And then you see it's sphero obj. I spelled this wrong. And then otherwise it looks like it's fine. Looks like it's fine. Now, I don't really know what I expect to happen here. Or just use prototypes at the top of the file. Yeah, but I don't want to. But you're right, that would solve my problem. Okay, so does this build? That's question 1. Yes, it does, it looks like. We're gonna have to restart our virtual machine to load the new kernel. And surely something is gonna fall over here. Presumably the mmap call is not going to work, is going to be my guess, because we have not implemented mmap for our GPU back buffers. So I expect no like kernel crashes. I do expect our application to return an error on dumb buffer creation. So let's see. So he reaches unreachable code at mainzig 86. So let's see what's in there. This is already open, but fuck it. Yeah, so he's crashing on the mmap, which makes a lot of sense. It's a little surprising that this is still working. A little surprising. So can we look at what's going on there? DRM ioctl. There's this like map dumb. So here he calls into. Do we implement this? No. So he goes into here, which I guess I see why. Like, I guess this doesn't do anything driver specific. He kind of just uses like generic gem stuff, I guess, which is a little surprising. Okay. So does that mean our map dumb? Well, does that mean when we create our GPU object, maybe in here somewhere, we are supposed to define some memory map calls? I think we saw that in here. There's an mmap function here. So if we write in here, we just take this mmap function and we say like sphero gem object mmap, right? Oopsies. Let's just see if this gets called. That's probably where we want to start. If this gets called, then we're on the right track. If not, we're gonna have to find it. So can we just do like print k, we were called. Dude, yo, pick up the damn phone, and I'm just getting spammed with like collaboration requests. No, I'm not gonna do that. I'm fucking busy, and since you're coming in here and demanding stuff from me, I'm gonna ban you. Thank you. Okay. Okay. So, and then I guess probably we want to like just like panic here. Is there like a die? How do we like crash the kernel here? I just return. We'll just return -1 for now. We'll at least see some effect. We'll at least see some effect. Bug? Yeah, that sounds right. We do need to say that we want like an mmap here. And he's mad. Oh, because I didn't put a comma. And then no trailing commas in this language, I think. So maybe this will be fine. Okay, and then we restart our virtual machine. So we'll go run. And what are we hoping to see? We're just hoping to see any evidence of our thing being called. test app dev DRI card1. We were called. Okay, so that's really good. That's really good. So we have proof of something happening. Okay, so I think that I wanted to look at there. I think I also saw some like VM operations thing. Virtual memory operations use mmap. So I'm not sure if this is required or not. Because I think that I was reading somewhere in drmmm.rst, DRM memory management. If we just look for like mmap in here, we see a little bit of docs that are probably worth reading. So we can read this. So gem object mapping, that's us. We are a gem object. Because mapping operations are fairly heavyweight, gem favors read-write-like access to buffers implemented through Java-specific hierarchals over mapping buffers to use space. However, when random access to the buffer is needed, direct access to the object can be more efficient. The mmap system call can't be used directly to map gem objects as they don't have their own file handle. Two alternative methods currently coexist to map gem objects to use space. The first method uses a driver-specific octals to perform the mapping operation, calling do mmap under the hood. This is often considered dubious, seems to be discouraged by gem-enabled drivers, and will thus not be described here. The second method uses the mmap system call on the DRM file handle. Yep, that's what we're at. DRM identifies the gem object to be mapped by a fake offset passed through the mmap offset argument. Prior to being mapped, a gem object must thus be associated with a fake object. To do so, drivers must call gem create mmap offset on the object. Right. So that's all been done already in our test application that we've worked on before. Once allocated, the fake offset value must be passed to the application in a driver-specific way and can be used as the mmap offset argument. Sure. So in the kernel mode setting, like flow, this is already all part of the flow and handled for us. The gem core provides a helper method DRM gem mmap to handle object mapping. This method can be set directly as the mmap file operation handler. It will look up the gem object based off the offset value and set the VMA operations to the type DRM driver gem VM ops field. Note that DRM gem mmap doesn't map memory to user space. So what is this? Gem VM ops. This might be more what we want. Let's look at that. Sphero-derv.c. So is that kind of like in here? Gem VM ops. Okay, where does like this thing live? Let's just look at like an example. Oh yeah, so that's what we're looking at. So these guys have done something very similar where they don't even implement mmap. They just implement the VM ops. And it sounds like from the driver documentation that the default implementation of the mmap function will do the right thing for us. And we just need to populate this thing. Let's see if we can prove that to ourselves. So if we look for references to this mmap call, he does just say, hey, okay, what was the function that he said that we could use instead? It was in documentation here. DRM gem mmap. So DRM gem mmap. Let's just see what this guy does. So he calls mmap opt, which is the function we were just in. Yeah, so if we don't provide mmap, he will just use the VM ops that we have associated with us. Sick. And he sets the private data to our object. Very nice of him. Very nice of him. All right. So we are in the right spot, but we don't actually have to do that. So then they're just kind of saying, here are the most interesting parts of that thing. And so I guess we could start here. The open and close operations must update the gem object reference count. Okay, that makes sense. Drivers can use VM open and VM close helper functions directly as open and close handlers. So we will do that because we are lazy. Then we will handle page faults. So when somebody accesses from virtual memory in the mapped section, that's when we can say, oh shit, we'll do our special thing now. Sure, should be pretty straightforward. Well, he says, not understanding anything. Should be straightforward. Shut the fuck up. Okay, So I guess all we want to do is we want to provide this VM ops thing. So we say is equal to Sphero gem object VM ops, I guess. And then we need that thing to exist. So I guess we do static const struct Sphero gem object VM ops. And then they were saying the open, close, and fault operations are the most interesting to us, right? Which I'm hoping it means that we can just ignore the rest. And he's saying that we can use the open and close derm gem vum open. Derm gem vum close. And then here we want Sphero. Why the fuck do they have struct in the name of their structure? This is like pin number. You don't need to write struct at the end of your struct, right? Am I crazy? But it's fine. So this will be called Sphero gem object fault, I guess. He doesn't like this, although this is fine. Oh, I need to put an ampersand here probably. Nice. Just do underscore s or underscore t. I think that just do neither. You have the word struct up front. If you're type defing, sure. But if you have the struct up here, then you're good. So we need to implement this fault function. And he's also mad about something here. No? I actually don't know what he's complaining about. He's saying that I need some semicolon somewhere, but I think he's high. So expected equals, oh, I did forget an equals, huh? Fine. Fine. If you're going to be like that. Now we need to implement this fault function. So Sphero gem object fault, and this is where the interesting work will be. So theoretically now, if we do nothing and return an error here, let's just like return segfault. Right, we'll just kind of like say, hey, we fucking segfaulted. Then what should happen here is that our application should actually succeed to map, but it should segfault when it actually tries to write to the buffer. If everything lines up with our understanding, which it might not, right? Who fucking knows? Who knows? But I think it's good to like theorize about what you expect to happen first. What's it bad about? Unused function, gem object and map. Oh, that's true. I think it's nice to theorize first because it forces you to like to make guesses. It forces you to like try to understand what's happening instead of just like blindly following. And then when things don't line up, then you can go like, oh, my mental model's wrong. What needs to get fixed? Okay. We will kill our virtual machine and we'll run it again. And we will wait 4 seconds for it to boot. The 4 seconds is annoying, but it's way less annoying than it used to be. It used to be really bad. Okay, so we do see a segmentation fault at this address, which is really good. And in main.zig, okay, I guess I don't have it open, fine. What was it? Is line 55? This is exactly him first attempting to write into the buffer. So that's really good. That's really good. That means that everything is lining up for us. So now the question is, what the hell do we do here? Right? So I have some notes here because I was researching this a little bit this morning. Eventually I came across this like this page. Oops, that's not where I want that opened. I want that opened here. So this is on like, I think it was like LWN device driver memory guide or something. Linux device drivers is probably where this thing was. Yeah, it was the Linux device drivers, and then I found this like memory mapping chapter. So that's what's open here. And in here, they talk about how this stuff is supposed to be implemented, But the interesting thing here is like we want to remap PCI bar memory, which is a little odd because it's not just like typical memory. If you look at like implementations of this thing, this is where I started. I only found that page and the thing after. But if we just look for like someone's implementation of this thing, what I think maybe I looked at like this one. We see them do this like some sort of like PGT thing, page fault, page number. Oh, I think I actually looked at the VirGL implementation. I think that's probably where I was looking. I'm pretty sure I fucking saw one in virt.io. Although that doesn't seem to be in my references anymore. Maybe it was here. Yeah, here we go. So derm, gem, shmem, ops, they have a fault function. This is where I was looking. So they basically just say the only like important piece here really is this like page to PFN thing. And then they have this like in this page they talk about mapping somewhere. Mmap device operation. Here. There. They said the job of handling new page tables is to map a physical addresses by something remap pfn range or something. So do we see that in here? We say VMF insert pin. We see page to PFN. So PFN's a word that we're seeing there for sure. And we'll see if down the call stack, if we see something that looks like that remap pfn range thing. Which I'm not convinced I'm seeing that. But can we look at like remap pfn range? Is that like a thing that's called in other places? So we do see some sort of like mmap based thing where they are calling that here. So I'm not really sure. I'm honestly not really sure. But my guess here is that we are supposed to find the physical address of like a thing and put that in the map. So maybe as like a stage 1, maybe we just malloc some memory ourselves and try to use that. So I think that we want to allocate like one page. I think I saw when I was like skimming this and kind of like or like maybe it was in other implementations when we looked at like when I looked at this, I see like pages are calculated by doing like a size of the allocation shifted right by the page shift. So I guess this is probably interesting. So the size of the object is what the size that they expect. Okay. So we probably are looking for, they probably have allocated a dumb buffer. So we probably want to extract our dumb buffer from this thing. So I think they said like they had like private data on here, right? Right. What did this guy do? He extracts the DRM gem object from the private data. Then he looks at the shmem version of that thing. Okay. And then he looks at the object size to get the page shift. Okay. So we can do something similar, probably. I don't know. So we'll like be like, yo, I want this thing. What's a VMA? We have VMF. Their VMA comes from VMF, VMA. Okay, so we'll do that. So this should be the same for us. And then we want to use the object size to get the number of pages. Or I guess we want to do kmalloc. Yeah, let's just start by mallocing something. Do we have kz alloc in here? Okay, let's do that. What distro do you use? He built his own. That's a funny answer, but no, that's not the case. I'm on Nix. So we want this to be allocated by obj size. And then we want to say this is our pointer. Okay. Then I guess we're gonna do something like try to get the physical address of this thing. So I think there's like vert to phys. I'm not sure if this is what we're supposed to use, but I think it is. So this returns a virtual address to physical address. So can we look for other usages of this thing? Does vert, like, are we allowed to use this on like a malloc thing? Like this thing is just like a context that they get. Who knows? Who knows? Let's look for like just like we're just gonna like try to see like where this thing comes from. So this comes from IO MMU allocated pages. Okay, let's look for another one. Actually, I think that I saw the reason that I'm just think it's okay to do this is because I think I saw in this thing. Maybe it wasn't here. I saw somewhere when I was Googling this morning that like this is a thing I can do. Maybe it was in like Linux kernel mmap kernel device mmap driver mmap impl or something. Nope, this isn't what wasn't it. Kernel device driver mmap. Maybe it was this memory mapping. This seems like where I probably saw this. K malloc. Yeah. Memory allocated by K. No. Yeah, here we go. So here he talks about like mmap here and how the memory should be allocated by a device. A driver should allocate memory using K malloc. Then map it to the user space as indicated by the VMA parameter using helper functions, such as this, which is lines up with what we saw in that book. And here he called vert to phys on kmalloc area. So I think that's a good sign. A good sign. Yes. Okay. So this is the physical address of the thing that we're trying to allocate, right? And then they have this like PFN thing, which is page frame number, I think. And I saw in a diagram somewhere, probably this one, where your address is basically just like your page is just like the top bits of your address essentially, right? You can like directory table offset. So basically you just like truncate the bottom bits and you get the page. So we should be able to go like phys adder is shift left right by page shift. Should be this. I forgot everywhere that in this language you need types. So pointer is going to be a void star. And phys adder is going to be probably also a void star. This returns a phys adder t. Let's do that. Phys adder t. I guess we want void star here. Then we want the page frame number to be something. So they talk about like remap page range, remap page, remap PFN range. Here we go. So this guy takes in a PFN unsigned long. So we'll call this unsigned long. I can't remember if I answered this, but someone said, been watching these on YouTube. Cool, you guys live one. It's glad to have you. Glad to have you. I can't remember if I answered that. I read it a while ago, and I might have just forgot to answer because it's hard to remember. And so what does this guy take in? He takes in the address, the area, the size, and protect flags, I guess. So you're not PFN range is for mmap. I think you're punting fault. Maybe, but we'll see. It seems reasonable in my mind to say, hey, I want this thing to be, I want to set this page as, I want to map this page. I don't know. Seems reasonable to me, but it does kind of seem like it could be wrong. Could be wrong. Adding VMA operations. Open, close. The more interesting thing I want is fault. Let's see if they have like fault in here. Remapping RAM with no page to deal with faults one at a time. I mean, we could also look at like what the other driver does. We could look at what gemshmem does. So great, we had an option there, or yeah, here, fault. So that is true that they are calling something else. So can we look for VMF insert pin or something in here? That doesn't exist, but like, what is this? Or just because I spelled it wrong. VMF insert puffun? Nope. Insert a single page frame number into the VMA. So maybe this makes more sense. Similar to VM insert page, this allows drivers to insert individual pages that they've allocated into a user VMA. Same comments apply. Okay, what's the difference? What's VM insert page then? Insert a single page into user VMA. This allows drivers to insert individual pages they've allocated into user VMA. This takes a source kernel page, which I don't really understand how we get that. So maybe that comes from like, does that come from like vert to page? Yeah, it looks like it, huh? So we could do it that way as well. Sure, I'm down to just try it and see what happens. So we have VM insert. Fuck, where was that? VMF insert PFN. Okay. And he wants the VMA, the address. And what does this address come from? VMF address, okay. Sure. Now, how do we prove that this is right? How do we prove this is right? Also, like, what else were these guys doing here? He's doing some like locking on his memory that we don't really care about. Page offset. Sure, doesn't really matter here. I don't think. Address minus start. I guess we probably do want that. Right, so we probably want to know. Yeah, we do want that. So we want the offset into this memory. So we have like our pointer allocated, which is for everything. So really this should be allocated one time. One time. But instead what we'll do is we'll allocate one page here. I think that makes sense. Page size. Yeah. So we'll allocate one page at a time every time they fault. And then we'll just map the whole page in. So there's no like offset handling to be done right now, which is fine. We'll figure that out in the future. We should be able to just go like this, right? Yeah. Sure. So we allocate a new page, and let's fill it with something. Memset pointer with like a number of like, you know, AB for page size. Right? So we'll just like rip ABs into this thing. And so then we can read the memory that we mapped and see if it's full of ABs. What are you doing? We are trying to we're trying to map GPU memory directly into user space process. And so we're trying to understand the like fault handling logic here, right? So we go into our application says, hey, GPU driver, could you give me some memory to write to? Then we go, okay, here it is. Mmap our driver at this position. He calls mmap on that thing and gets like a pointer. And he can like write and read to that point, to like a pointer that he got back, right? So he gets back like 0x1234 and I'm like 100 megabytes long or something. But at that point, nothing's actually like when he writes that, what actually happens? Well, we try to map some memory, physical memory to that location, and that's what we're trying to understand right now is like what is the API for that thing, and then eventually we can like hook that up to point to GPU memory. But for now, he just points to something that we're allocating right here. So I believe this should be fine. And I think that when we call mmap now, are you making your own? My own what? Probably the answer is yes, but it depends on what you mean. Okay. Then in our test application, let's start by just, instead of trying to draw anything, let's just try to read some of the pixel data. So can we say like print stood debug print? Probably in hex makes sense. And let's look at like pixel data at like offset size over 2, right? Just kind of like poke a random spot in this thing and see if it's full of ABs. Sure. That seems reasonable to me. So let's run our thing, test app, and run zig build, but we have to turn on networking first so that we can upload our new version of the application, which we are doing now, and we are hoping to see something. But instead, we see index out of bounds. Because this has to be over 8. Because it's 4 bytes per byte, or 4. Okay, so now he's mad that he cannot map. Dumb. I'm not sure why that's the case. Since it successfully mapped before. So I'm just going to quickly restart the VM just in case there's some sort of like statefulness to that thing. Have you done CMD stuff on your projects? I've done a little bit of Neon stuff, not on stream, but I have played around with like vectorized instructions and stuff before, but I haven't, no, I have not done like a stream on it or anything. Okay, let's try one more time. Zig build and run this thing. Okay, here we go. So now we did get something, but he doesn't like what happened. So there's a null pointer dereference in the kernel. Coming from somewhere. I don't know where. That's interesting. So what is the easiest way to debug this? Handle fault. Page fault, oops. So does our driver even like, does this happen? We're faulting. Right, let's just start here. We tested this already, right? Because we returned a seg fault here. Right? We returned. I thought we did. Let's double check. VM fault sig seg v. I think we did this already. But let's double check. Because something's not working the way I expect, and so we need to walk back a little bit. Okay. You need to return a proper VM vault value, not 0. That's possible for sure. Oh yeah, so we got we're faulting and seg fault. Great. So you're claiming that I need to return something, which would be reasonable. I thought they all looked bad. Right? Major, page read from storage. Completed, fault completed. So is that what we want? I guess we'll look at somebody else's implementation of this thing. So we were looking at the gem shmem helper as a reference here. So he returns ret, which comes from here, which comes from here, which says comes from here. And he returns something. If it's not none, okay, finally map the thing, so he gets entry here. And then out unlock, he just calls VM fault no page. What does that mean? Fault installed at the PTE, not the return page. Physical table entry, maybe? But that's because this guy's calling PTE. Which I guess is what we're doing. Oh, I guess we just return what they're returning. That's what we should do. Let's just do that. That makes more sense. That makes more sense. All right, what happens now? What happens now? Root, test app, dev, DRI card 1. We see a lot of spam of we're faulting, which was a little annoying. And then a seg fault in our GPU, or in our virtual machine, which isn't really great. Probably in here, we want to say if we want to probably return after this. To avoid like spam somewhere else, because what we're doing is wrong. Right? We know what we're doing is wrong. We're allocating every time somebody tries to touch the memory, which maybe we're like running out of memory on like the virtual machine or something, which is causing problems. Definitely a possibility. So let's make sure that we are only poking the memory one time. So we upload the latest and greatest. And there we go. That's a really good sign. That's a really good sign. We see some AB, 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 ABs in there, which means that we probably did what we wanted. Okay, that's pretty sick. So we kind of did this at some point, and then we at some point started doing like implement proof of concept mapping mmap to kernel memory. And then now we are probably going to be doing something that's like actually map GPU memory. That's what we're doing now. So let's try to just map anything from PCI memory. So what we're gonna have to do here is we're going to want to go into our like virtual machine implementation, and we'll like maybe allocate a buffer over there. Which we did, right? When we said create DOM, we have a buffer allocated, which does a gem funcs. Wait. Where's our actual... We don't actually do the allocation here. That's kind of funny. So we actually only support create GL text, which is not really what we want. We kind of want to just allocate a buffer. So does create GL text, is it special? Probably not. Maybe we readjust this command to just be like create GPU object for now. Seems reasonable. Seems reasonable. So let's maybe go to our QEMU shell so that we can do some QEMU development. And we will add a new command to our GPU to just allocate a GPU backed buffer in general. Source QEMU. Okay, and what we'll do is we'll say fix me replace with generic buffer allocation, but we'll leave it in here for now. And we'll say I would like to allocate hardware buff. Right? Seems reasonable. Seems reasonable. And if somebody calls allocate hardware buff, they're surely going to want to do something. I don't know what yet, but surely they're going to want to do something. Alloc hardware buff. So presumably we're going to have the hardware ID of this thing. We're gonna have like uint64 t star hardware ID. Then what? They're gonna have like the size. Probably. And is that it? Probably. Probably. So I guess we will do the same thing that we did for texture allocation, where we malloc a thing. Oh, I guess that this texture does stash the width and height. So there is actually a reason to do it that way. So we will instead, I guess we need like some sort of hash map. We'll call this DOM buffer, I guess. And we'll do the same thing that we did here, where we stash in this thing just a malloc buffer. I think that makes sense. Okay. So he wants a size t, so what can we do? Size t like this. Okay. Sure. Yeah, seems reasonable. Seems reasonable. Then let me think for a second. I guess we'll start here and figure it out as we go. Okay. Let's compile. So now our GPU should have a command that he can run, except it's broken. Because why? What's he pissed about? Needs a different size? That's a really good point. It's a pretty good point. Pretty good point. He's mad about this unlock thing. Wait, why? Oh, because I probably need to put an ampersand? I did. This is a QEMU Oh, I didn't break? Is maybe what he's bitching about? Noise, that makes more sense. Okay. Okay. And cool, I guess that's kind of our starting position. So here we're gonna be like, yo, I'd like to allocate a hardware buffer, please. And here we create our dump object. And then we actually have to assign him somehow. So we're going to go like, I guess whatever we did in the other version of this, where we send a command. I guess we're going to do the same thing. Where we don't have parameters here. Here our args are just the hardware IDs. This makes sense. So our obj is going to be called sphere objects. Let's just do this. And then we just have size. So like this. And then the command is, did we paste it already? Yeah, it's alloc hardware buff. Alloc hardware buff. What the fuck? Uh-huh. Okay. Seems reasonable. So at this point now we have a buffer that we can ask for. And then what were we doing? We were in like the mmap implementation, right? So here when we fault, we want to like get our object, which is going to be a sphero object like this, which is going to be a container of from base struct drm gem sphero obj. And now we're gonna have to like create a command to actually do the mapping, right? So we're gonna be like, yo, I have this obj with this hardware ID, right? And GPU, I want you to map that. So we're gonna make a command that's like map hardware buff. Okay, so our map hardware buff is going to probably take in the hardware ID as well as the offset. Into that hardware ID, into that hardware buffer, as well as the destination page. So we can probably do something like this. Okay. We're going to look up this thing. So we're going to be like g hash table lookup from our hash table and this thing is going to look like this, okay? And what's going to happen here? We are going to take the offset and put that into a page table somewhere, is my guess. That's kind of my guess, is that we're going to have like uint, what's like our like pointer type? Void star, yeah. Pages. And how many pages are there? What's like PCI bar max size? I think it's like 256 megabytes. Without resizable bar. PCI bar max size. Let's Google it maybe. Bar. Okay. Each bar describes a region that's between 16 bytes and 2 gigabytes in size, blah, blah, blah. Classically, bars were limited to a size of 256M. Okay. So we can say 256 times 1024 divided by 4096. We have 64 pages. 64 pages that we can work with. And what we want to do is we just want to like map our pages directly. If I write it like this gets oh, you know what? That means when we sorry, I'm thinking for a second. Okay, this is fine. So we have 64 void stars here, which are going to point to our actually allocated buffers. Yes. So when they call map, we're just going to say pages at dest page is equal to buff plus offset. Right? That'll give us a pointer to write to. And now what we have to do is we actually have to implement the writing of that thing. So when somebody writes that memory, first of all, we need to like create a bar for that stuff to live in. So can we do like, this is going to be our mmap ops, mmapped bar, mapped GPU mem ops. Sure. This is going to be 256 times 1024 size, because that's the maximum size. And we'll call this GPU mem. Okay. So this needs to go into bar. This needs to be like a memory region of GPU mapped. What do we call it? Mapped GPU mem. Okay. Okay. And then we just have to implement this thing, I guess. So we're going to say that when somebody tries to read from our GPU map memory, we basically just look at the page, I think. Mapped GPU mem write and mapped GPU mem read. Okay. And this is the signature. Mapped GPU mem write. And read is going to be mapped GPU mem read. Okay. So they have the address and the size. So when we work with this, the address is relative to the base. So we just say page. What is a hardware adder here? This is just a UN64 or something, yeah. Page is equal to adder divided by page size, right? Okay. Do we have 496 name notes in here? No. Okay. Then we say we get like a. I assume that we just do here is us and pages at page. This is the base address that we're trying to read from. Right? Now the offset is going to be the address percent page size. Right? And we should just be able to be like, can we just be like base adder plus offs is equal to whatever they fucking wrote? I guess we need to know the size of their write, which I assume comes in here. I assume that's what this is. Size is in bytes. Yeah. So depending on the size, we need to reset just that segment of memory. So we want to do like 1 shift left by size is the mask. Right? It's like something like this. No. That's not right at all. Yeah. So size is in bytes, number of bytes. So if we're writing 1 byte, we want 0xFF. If it's 2, we want 0xFFFF. 3, we want this much, right? So I think this is right. Times 8. Is that right? I think so. Yeah, that sounds right to me. So size, because this will shift 1 will shift me left by 8, 2 will shift me left by 16. And this is 16 bit. 16. Yeah. That sounds right. Then we want to do like unit 64T star elem or something is like the base address plus the offset. And then we want to do like hold on. we want to lm and equals mask, the inverse of mask, right? So we want to zero out anything underneath the FFs, which a bitwise not will do, and an and will do. Okay. I think that's right. Then we should be able to do like lm or equals data and mask. I think that's right. I'm like 70% sure that's right. 7% sure. Right, because what I'm expecting here is that like they come in and they say, I'm running 3 bytes. So we should zero out the bottom 3 bytes and then replace it with what we got. Which I think this does. Then on read, we're kind of going to do like a similar thing. Kind of like all of this is the same. But we just return lm and mask instead. And here we're just gonna put like fix me mega duplication with write. Okay. That's like a maybe. That's like a maybe that works. So what this should do is we register pointers with our page list. When they try to read and write from the paged area, then we look at the pointer the pointer that page points to, and look at the offset and look at that specific byte. That's like a maybe. That's a maybe. We have to initialize this bar, which we do here. Do we want to? We probably want to null check this thing. But we won't. Fix me null check. Kind of handle that later. And I guess let's just start with trying to map a page. Okay. Okay. So we added a command. Map me this object. Okay, so we're going to take this and stick this in our kernel thing. Okay, and then when we execute our fault, we're basically going to ask it to map that hardware ID, right? So what was our command here? It was hardware ID offset destination page. So this is 1, 2, 3, 4, 5. Okay. So it's S. We need our priv, our class here. How do we do that? Is it in like gem object? Gem device, yeah. So it's like gem device. Gem dev is base dev, and then struct sphero priv is a DRM dev private data. So now we should be able to go like priv regs 1 is equal to object hardware ID shifted like this. 2 is this shifted right by 32. 3 is going to be the size that we are mapping. However, this is just always one page. So it's actually the offset. It's the offset. So what is our offset? Our offset is like DRM. It's going to be like from the request. It was like something minus VM start was what we saw before, right? Yeah, VMF address minus VMA VM start. Okay. But this is a page offset. Well, that's fine. We can do address offset. That's fine. So this is a U64. Okay. Is that right? They have an offset and a destination page. This kind of feels like it should be a page offset. Kind of just feels that way. Which page are we mapping? Yeah. So this address, this should tell us which page we're mapping, which means that here we get page offs, and here we have our destination page, which will just kind of hard code to 0. Okay. That's like a maybe. What do we call it? Map hardware buff. Okay, so we fucking run that shit. Then we should have more IO memory. That's going to be the mapped GPU memory. Okay, so however we initialize this regs shit, we are going to want to do something similar. Where we do the same thing, but for GPU memory. So this is 256 times 1024 megabytes, and the PCI address is going to be mmap adder, or GPU map mem adder is the second device. Okay. Everything there feels kind of okay. Probably we have to unmap that thing as well. Okay. And did we assign this to PCI bar 1? How does this get assigned a bar? Oh, here. Okay. That makes sense. That makes sense. Okay, so we have this bar. He's mapped now. And we should be able to just fucking rip that shit then. Right? So when we have our page fault, we need to get the physical address of this mapped memory. And we saw, like, I had written down from before that I wanted like IO remap page range or something, but that's not what we want. We want like the equivalent of this. We want to figure out how to get the IO address as a physical address. So is there something like, is it fair to call virt to phys on that thing? Probably. We're accessing it like it's just virtual memory. So can we just call this on our like S? Do we have priv here is what we're calling it? Map GPU memory? That feels like it might work. Right? And so like unconditionally, we just map that thing. Now, we probably have to unmap whatever was mapped before. But we'll ignore that for now. We will not do this malloc anymore. We don't need that. And this should be fix me use like a keep list of least recently used pages or something. Sure. That seems reasonable to me. Here we should probably be like plus page num, and then we'll just say u64 uint32. There we go. That way it'll be easy to fix. And we'll call this like desk page number something. Okay. In page. Sure. Yeah. All that seems like it might make sense. Maybe. Let's just fucking run it and see. We'll just fucking run it. See what happens. You never know. Okay, so I think we need to rebuild our QEMU as well. Okay, he's mad because page offs. Offs undeclared. Bump, 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 bump. That feels right. I'm like pretty unconvinced. I don't know how to like test this effectively yet. We'll kind of figure that out as we go, I guess. Okay, so we're gonna run this, and our test right now just tries to read memory at some location in that thing, right? So how do we test? How do we test this is reasonable? I don't know. If we run this right now, he does just like fucking crash. So this thing's mad because the hash table was not initialized, and then everything else is probably crashing from there. Okay. So that's a good point. We probably just forgot to set up our dumb buffer table. So let's try that again. It's fair, it's fair. He's mad at us because we're trying to use uninitialized memory. Fine. Fine. If that's how you're going to be, that's how you're going to be. We wait 4 seconds for our computer to boot. Morning, morning. And let's try again. Okay, so this didn't crash anymore. This thing's still mad. He's saying bad page table, corrupted page table address. So that's probably this failing, right? Which means that like maybe this isn't okay. What does like iremap do? You know, like what? What's he really do? Blah, blah, blah. I don't see any implementation here, which is kind of fun. Can we like ask like the idiot? Can I call vert to fizz on iremapped memory in the Linux kernel? Question mark. He should tell me no. That's good. Instead, you should use the original physical address that you use with iremap. Oh. Okay. That sounds cool. I like that. Iremap just returns a virtual address to access the bar. So here, the PCI resource start here should give us a physical memory, is kind of what he's claiming. So like we have like PCI dev resource start resource size T. So this is a physical address. Yeah, okay, okay. So we don't do mapped GPU memory at all. We just instead store a fizz adder T to the mapped GPU memory, we'll call it. That seems reasonable to me. So now we just don't do this. We just do this. then everything else just works, right? There's just no vert to physical here. This probably needs to be multiplied by page size, even though it's nothing right now. Probably, but let's try that. Let's try it and see what happens. He's mad because our remap is, this should just be like here. We have no IO remapping to do. And then run. Crimson Dawn, how do you know all of these answers already? I suspect that means that you're like comfortable in kernel development land. Or you've just been Googling docs like crazy. I'm curious what you do. Okay. So I can't do this mapping twice. He doesn't really like that. But on the first map, I did get something out. It was like kind of like garbage memory, which is hard to prove that we did the right thing. So maybe what we'll do is in our test app, what if spend a fair amount of time looking at kernel code before? That makes sense. Makes sense. Probably where we were doing this pixel data here, including DRM specific code. That's sick. It's kind of fun. So can we look at like pixel data at offset? Like, we'll pick an offset into the buffer. So at offset 2000, we're going over 4 because we're at pixel data here. And 2000 is divisible by 4, so we're chilling because we're looking at like a U32 slice. So if we do that, let's in our QEMU stuff, maybe when we allocate DOM, allocate our hardware buffer, can we just say like if size is greater than 2000, greater than or equal to 2004, can we do something that's like buff at 2000 is equal to AB. This is AB CD EF 01 or something, right? Let's just see if we see something that resembles those numbers. Oh, I guess we probably want like A, B. How are we print? No, we're printing it as a hex number, I think. Yeah, we are. So let's do that. Let's do that. Okay. A, B, C, D, E, F, O, 1. Okay. Let's just see what that gets us. We're hoping to see a number that resembles that in any way, shape, or form. If we didn't, we're gonna have to get a little more clever with our debugging, but we can always get to that later. Okay. Do you think I should learn C before learning Zig? I've been in software engineering using Golang and JS front for like 4 or 5 years professionally. Never really learned C or C++. I think that you'll learn similar concepts by doing them both. I think Zig will kind of catch some more foot guns, but C is definitely applicable to everything, right? C is definitely like way more like widely applicable. But yeah, I would probably go C if it were me. But I think that you like both will be fine. Both would be fine. Okay, let's get our networking up so that we can upload the latest version of our test app. We run that thing. We see his output. We see 0x zeros. So that's not great. So I guess we need to start adding some logs to here, probably. So let's say we have allocated buffer at this memory location, okay? Then this stuff gets at 2000, that makes sense. And when we're calling map hardware buff, we're going to say printf mapping hardware buff with page this to page this. Okay. And this is going to take in with page offs to dest page. Okay. Then we will say page is mapped to address this, which is going to come from all of this stuff. Okay. And why is there an insert here? This is fucking stupid. We're being a dumbass. Not that it matters, I don't think, but that shouldn't be there. Okay, and then what happens on read will be like reading from address this. And then with mask this. Okay. And then uint 64t ret is equal to this. And then can we just say that we are like value masked is this, unmasked this. Let's start there. So this is going to be ret and ln. All right. That should give us a bunch of info. I need to do lx, really? That's fucking annoying. And I knew that. Of course I knew that. Mask also lx. All right, let's see what happens. Let's see what happens. Zig build. No, run. All right. Let's see what he says to us. Let's see what he says to us. Root test app dev dri card1. Okay, so we have allocated a buffer at this location, mapping hardware buffer with page 0 to page 0. That makes sense because 2000 bytes offset is within the first page. So this seems correct to me. Page is mapped to address this. Okay, reading from address. This seems wrong to me. Page. Hold on. Let me think for a second. Page is mapped to addresses. Okay, that makes sense. Reading from address. This should be plus offset here. Yeah, that makes sense. So let's do it this way. Reading from address lm with mask this. Okay, let's see what that looks like. Let's see what that looks like. Okay, because this is an obviously wrong log, but it's kind of reasonable given that we didn't actually ask it to print the right thing. Okay, root test app dev dri card1. Okay, so page is mapped to this. So we allocated a buffer at this address, sure, and then he is reading from this address. So can we do like this minus this should hopefully be 2000. Nice. Okay, so that's a really good sign. With mask 0x0. This is the problem. Our mask is wrong. So what's going on here? With mask this from size this. Is the size coming in at all reasonable? Because if not, then we have a fucking problem. If not, we have a fucking problem. Okay. From size 4. Okay, so we've just fucked up our math here. I could have sworn that was right. So 4 times 8 is 32? Is this all in 32-bit math? Is that why? Is this like some like bullshit? 1 shifted left by size times 8 is just going to be 0, I bet. That's my bet. That's my bet. Which means that you actually probably want to do like bitwise not of 0. And then shift it right by 64 minus size times 8. 1 UL. Oh, thank you. Is that really how you fucking... C UL suffix. Okay. I didn't know that was a thing. But that probably makes this work better. Let's try that. If so, you are a kind sir. You can tell my C is not very good because I'm just throwing shit at the wall. It's nice though that like we can at the very least break down our problems and make good guesses about the mistake. So yeah, there we go. That's much better. Oh, that's the fucking number, dude. That's the fucking number. Look at that shit. Look at that shit. Right? Because that's what we wrote in here. O1, A, B, C, D, E, F. Except, or sorry, A, B, C, D, E, F, O1, except it's going to be backwards. So it's O1, E, F, C, D, A, B. O1, E, F, C, D, A, B. So that's very good. That's like really, 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 really good. That means that the read is working correctly. I think that we had to mirror a fix somewhere in here. Right? This mask needs to get applied here. Did we change anything else? Base adder plus offs, mask. Probably fine. Okay. So can we then write and read something back? Let's see. Let's see. Let's do similar logs here. Writing to address this with mask this and new lm is going to be this. Sure. Sure. Let's see. So we're gonna build QEMU. We're gonna build to QEMU. And then we are going to update our test app to try to write to that memory a little bit. Let me think for a second. Yeah, let's update our app to write to that memory. So we'll just be like, pixel data at 2000% 4 over 4 is equal to 0x1234. And then we'll read it again. Sure, fuck it, you know? So we go back, run, put it in the background. We need to upload a new version of the app with the right attempt. So we turn on networking so that we can upload our thing. And let's see what he says. Okay, so did I write reading on both sides? No, I have writing to address. Why don't I see that here? Oh, here, because I forgot a new line. Okay, sure. So here we are writing to that same address with this same mask. New LM1234. Seems good to me. Seems pretty reasonable. Seems pretty reasonable. I'm pretty happy with that. Pretty happy with that. Okay. Okay, so I wonder if that means that we can just kind of like run it the way we were running it before. Like, can we just like render our frame buffer now? I guess that means in the Linux kernel, we're going to have to use dumb buffer as frame buffer. So what is going on there? So in our kernel driver, we like create the dumb buffer, and then when we get into this thing, we just say set hardware frame buffer, which he assumes is from the textures, which is problematic. Problematic because we didn't allocate this thing as a texture. We allocated him as a dumb buffer. So what does that do on the other side? Hold on, just give me a sec here. Set hardware frame buffer. So he does extract the width and the height here, as well as the stride from the texture. So how does that get handled? We must have to do something like add FB. We probably take the dumb buffer and we turn him into a frame buffer somehow. That's my memory here. And this frame buffer is the thing who owns like the metadata. Right, so it's this. Add FB goes to add FB, goes to add FB, goes to internal frame buffer create, which calls RFB create, which calls GPU frame buffer create, which looks up the object and creates the DRM frame buffer structure. So I guess like technically here we would want to like create GPU object which maps which holds frame buffer width height stride. But for now we can probably cheat. And cheating is great for us. So can we just say like set DOM frame buffer? Okay. And if we do set DOM frame buffer, it's going to look very similar here. Except we'll just hard code the width and height. We can't fucking do that. It doesn't even solve our problem. But it's a good intermediate steps. It's fine. It's fine. So this comes from the DOM thing, and this is now just a void star buff here. Our width is going to be 1024. Our height is going to be 768. And our stride is going to be 1024 times 4. And our data is going to be buff. If this works, then we are fucking chilling. Then for now, we can just say if we're dumb or not. For now, it's not ideal, but it's fine. So say bool is dumb here. And create here. We will say, first of all, is this thing zeroed out? is kzalloc. So is DOM will be false by default. So here we can just say obj is DOM is equal to true. And then when we try to do our plain update, i.e. ask it to actually show the fucking thing, we will do this. So we'll say if we are not DOM, here we can assume that we have this. We'll say if not sphero obj is DOM, we do this. Otherwise, we do this. And this is going to be a sphero reg command set DOM frame buffer, which we need to add here. Set DOM FB. Is that what we call it on the other side? Not that it matters, but yeah, it is. Okay. Sure. Sure, if this works, we are fucking chilling. Let's see. Ninja make close this, run again. He's mad because I'm in the wrong directory. Okay, okay. Root, test app. Nope. UDHCPC. All right, moment of truth, baby. Moment of truth. Okay. You know what? That's not that bad. It's definitely yellow. It looks like there's some sort of like mistake. Oh, that's just the size of the thing. That's probably fine. Okay. Okay, so I think now the problem is probably unmapping. Yeah. Yeah, that's probably a little bit of a mistake. So I think that we have a good initial spot, except I think that probably we are not handling the fact that we have to unmap pages. That's not handled. So for now, we're going to do something like, there's got to be like an inverse of this thing. VMF remove, VMF insert. Oh, what's this? This is a simplified this for common driver use. Sure, okay. How do I mean, we're getting distracted though. How do we like remove? How do we remove? I wrote 758 instead of 768. Oh, I did? Dude, your eyes are sharp. Good eye, good eye. Not that that really matters. That's probably not, I mean, we're not seeing like eyes or anything, so I'm pretty sure that that's a problem, but as this is called only for pages that do not currently exist, we do not need to flush old virtual caches with a TLB. So is there like VMF replace? Okay, let's see. We'll ask the idiot on ChatGPT. You know, he's sometimes got some ideas. Sometimes. Is there an inverse function to this in the Linux kernel? Question mark. If I want to replace an existing mapping. If I want to remove an existing mapping because the backend is no longer hooked up, right? Is that doable? Blah, blah, blah. Remap Puffin VM unmap. Unmap a range of virtual addresses. Page remove. You can map a new PFN like 0 or page none to effectively remove the mapping. Okay. Sure. VM unmap. This function can be used to unmap a range of virtual addresses. If you have the range of the mapping you want to remove, you want to make page table entries. Um, remove mapping takes in a VMA. So what is the VMA for in his fucking example? Okay. Can we look at the gem shmem helper? I guess they're kind of doing something like fundamentally different from us. Fundamentally different. VMF insert. What is it? What's the other similar one here? The other function, VM insert page. Okay. So this allows drivers to insert individual pages that validate into user VMA. The zero page is supported in some VMAs. Page has to be a nice, clean individual kernel allocation. If you allocate a compound page, you need to have it marked it as comp or manually just split the page up yourself. Traditionally, this was done with remap pfn range, which took arbitrary page protection parameter. This doesn't allow that. Your VMA protection will have to be set up correctly. This means that if you want shared writable mapping, you'd better ask for shared writable mapping. Usually this function is called from an mmap handler under mmap lock. So we can change VMA VM flags. What is the so why can't we just use remap? It seems like we can use remap within range in kind of like the same context. It's like the same concept. Okay. So what does this thing do again? We were kind of looking at this at some point. So he's saying that there's a special case here with page none. He's claiming that. Claiming. However, I don't really see evidence of that, to be honest. I'm not convinced I see evidence. Target page. I want to just like unmap it. Is that crazy? Because the problem here is that as we replace the GPU memory, like we can't. What we're doing right now is we have like GPU memory is exposing some stuff that internally is pointing to like objects, right? So you have like an object here, an object here, an object here. And the idea was that we like kind of point this here, point this here, point this here, right? And then in like our mmap, we kind of like point to segments of GPU memory, right? Now, right now, we're only ever using the first block of GPU memory, which should be fine. But it just means that like as we need to make sure that like in the future, the addresses that we're currently like if everything is pointing here, that's wrong. We need to kind of like like undo these connections every time we reset it. And so I'm trying to figure out how that works. You know, VM insert page. Like it just feels like there should be an equivalent, like an, remove page, delete page. I wonder if you can like set it to 0, kind of like like if 0 is like a special case. seems like maybe. Could be. Could be. So PFN here. I don't think memory mapping is supposed to work like that. NetMap should map the same memory. The fault handler just lets you do the mapping easily. Well, that kind of like undoes the whole idea. That kind of undoes the whole idea. If that's true, I kind of was banking on that being the case. Because we have only 256 megabytes of bar to map. And so I was kind of assuming that at some point, we have to be able to remove stuff. That was my assumption. I mean, virtual memory surely could work this way, right? I don't see any reason why we couldn't fault again later. I don't really understand why that wouldn't work. Maybe there's like caching implications there. I could see that argument. But like, okay, we can remove page kernel remove mmap entry or something. Kernel unmap page pfn. We'd have to do that manually, not via page fault. But during my page fault, like the page fault is the only time where I have to unmap something, right? Because like I am replacing another page, if that makes sense. Release. mmap maps to an external. When calling mmap with our own serial thing, we can invoke remap pfn range. Now the process got blah blah blah. So they're saying you could do this via release or munmap. This is close. This is pretty close. DMA unmap. Okay. Insert PFN. So what does this actually do under the hood? He ends up doing this like set PTE at. Map consecutive ranges to a contiguous range of addresses. Okay. Which calls set PTE, native set PTE. Native PTE clear is probably what I'm looking for, right? PTE clear. Okay. Wait, this looks promising. This looks promising. Oh, fuck. Where the fuck was I? Oh, God. PTE clear. I think you also made your bar only 256 kilobytes. That's a really good point. I did do that. That's true. That is very real. I guess none of these are really where I want to be, huh? Oh, it was the one in memory. It was the one. Okay. So does this go anywhere interesting? PTA marker clear. Page missing address. So this will never occur in our case. Which sucks. Okay, so set PTE. This is where we're set PTE goes to native set PTE, which has. I mean, this looks interesting though. Native make PTE of 0. So PTE 0 is the clear flag. So I wonder if we can just set our thing with 0. This is kind of concerning as well. The fact that he says you do not need to flush old virtual caches or the TLB, because I don't really understand what that means. But we will kind of think about that later. So for now, let's look at our sphero-priv structure. And for now, we're just going to say we're going to keep track of the pages that are allocated for now. Sorry, I'm just thinking for a second. The mappings are like per file per opened resource, which means that storing it in like global space is kind of messed up. But I guess it has to be. I mean, the like GPU memory is like a global resource. So for now, I'm just going to say page mapped page. This is fucking stupid, okay? Ignore this is like wrong. But this will hopefully let me work around the problem for now. I just want to see what happens if we do like priv mapped page. We are going to set this. Sorry, return ret to VMF address page offset, I guess. Page offset. Now we are going to check if the page offset is different than the mapped page. Which I know is wrong because the mapped page is, it's fine. Fix me, this is not right. The mapped page is stored globally, but the value is virtual address for this specific mmap instance or something, but it's fine. I understand it's wrong. I just want to see. So if this is different, then I wanted to try inserting I guess the old address. So this guy under the hood, he's working with address, which is kind of strange, not page. Sure. So can we like replace it with like priv mapped page shifted left by page shift to turn it into an address? 0? Like, this is kind of what I'm thinking. Kind of hand wavy. I'm hoping that that does something sane. Who knows, right? Who knows? I don't, but maybe. Yeah, okay. We shall see, and then we need to rebuild this as well. Rebuild QEMU, rebuild the world, and then we restart our virtual machine. All right. Let's see what happens. Root test app dev dri card1. All right. We are still seeing a big yellow blob. And what's interesting to me is that we don't see a change in behavior. Like, I guess the last thing we write is always yellow. The last thing we write is always yellow. So that kind of lines up. If we are always writing to the same memory location. So probably what happens is we write to every memory location as we rip through the thing. Then we probably get stuck writing to the last memory location over and over and over and over and over again. So probably if like on future frames, we try to write a different color. Right, so here we just say color is equal to a different color down here. I suspect that we'll see only like the bottom segment of the yellow page gets reset. That's what I suspect will happen. So let's see. CD to test app. And if so, we understand the problem, and I'm just gonna have to do some research offline, I think. Because I don't know how to fix it. So he's mad because color cannot be assigned to a constant. We'll just make this a variable, and that solves our problems. I guess that kind of makes sense. Because the two buffers are allocated back to back. It is a little surprising. That's not really what I was expecting, to be honest. It's quite surprising. Quite surprising. Okay. I will think about it. But for now, I think I am quite happy with this level of progress. It's 4 o'clock now, so we have made it 2 hours, and which is, I think, a pretty good time to stop. Yeah, and I think we actually got quite far today. We implemented like a lot, it feels like. Basically, we made it so that we could remap GPU memory. So we implemented like a fault handler for our specific buffer objects that allows us to gets forwarded to a request to our GPU to take some memory for an object that we've allocated and expose it through a PCI memory mapped region. The only remaining issue is that we have to figure out how to unmap sections, as well as track which sections have been used and stuff. We'll have to do some sort of like scheduling on the kernel. But for now, if we could just get to the point where we unmap that page every time that another page faults, so we could only ever expose one page of GPU memory at a time, that would be very cool. Very cool. So I'll think about it. But pretty happy with that progress. That's really sick. Really sick. We're close to being able to like arbitrarily map GPU buffers, which will be cool. All right. So I think we call it there. Thanks for watching, guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. 12:30 to 2, we are typically doing like cleanup and like unit testing and like research and stuff like that, kind of like supplemental content, I like to call it. And then from 2 to 4, we're usually doing some focused new feature development like you saw here. So if you want to check out those 12:32 segments, those are archived in YouTube member streams or on Patreon. Or if you catch us live at 12:30 Pacific time, that's great. Otherwise, don't forget to like, subscribe, Twitch Prime. If you're new here on Twitch, there's a YouTube link in the Twitch description. You can swing by where you can like see archives of our previous work. And if you're watching on YouTube, there's a Twitch link in the YouTube description. You should swing by and say hi if you feel like it. There's a GitHub link in the Twitch description where you should see this code eventually show up under GPU testing env. I think that is all we have to plug. YouTube, goodbye, and Twitch, let's find someone to raid.